Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This is the third lesson on vectors. We're going to look at scalar multiplication and linear combinations. So look at this expression. What do you think it means? So obviously when I look at it, what I see is that I have a vector, vector v, and it's multiplied by a scalar, simply the number 6. And the nice thing is that it means pretty much exactly what we hope it means. It basically means that I'm going to take vector v and multiply the magnitude by 6. So it's simply going to be a vector in the same direction, but 6 times as large. So just to visualize that, the rule says that when we multiply a vector times a scalar, it changes the magnitude of the vector. So here we have vector v, and I've just represented y by this arrow. So it's a certain magnitude, and it's going in a certain direction, roughly to the right and up a little bit. So if instead I have 6v, I'll end up with this vector. And as you can see, it's definitely in the same direction. It's just 6 times as long. And just to prove to you that it's 6 times as long, here's vector v, but I've placed vector v 6 times end to end, or tip to tail, because it's a vector. And we can see that this new vector, this purple vector, the 6v, is 6 times as long and in the exact same direction. So that's what multiplying a scalar times a vector does. And here's an example without drawing an arrow. So if we have a vector A and it represents a force of 350 newtons, and that force is acting at an angle of 40 degrees to the horizontal, we need to describe vector 3A. So again, all that 3A means is that we're going to be changing the magnitude, but not the direction. So the magnitude of the original vector is 350. So I need a vector that is 3 times the magnitude, but the exact same direction. So 3 times 350. So the answer would be that 3A is a force of 1,050 newtons, acting at an angle of 40 degrees to the horizontal. So again, you can see that the direction has not changed, but the magnitude is 3 times as big. So what would happen though if the scalar was a negative? So instead of multiplying vector v times 6, what if I multiplied by negative 6? So what do you think that would do to this vector? So again, the nice thing is that it's pretty logical. What happens is that it's 6 times as long, and it now goes in the exact opposite direction. So you learned about what opposite vectors are earlier in the unit. Opposite vector goes in exactly the opposite direction, meaning in 2 space at least, 180 degrees to the original direction. So originally it was up to the right, and now it's down to the left. That's what vector negative 6v. So in this case, it changes the direction, but only in the pure opposite sense. And again, if I line up 6 original vector v's, we can see that it's 6 times as long, and it's clearly going the other way. So in general, oh, wait, another example before we say in general. So here's a non-visual example. We have a vector c, and it represents a displacement of 400 kilometers to the east. We want to describe vector negative 1.5c. So we know that the new vector is going to be 1.5 times, 1.5 times the magnitude. So I have to take this number and multiply by 1.5. And because it's negative, it's going to go in the opposite direction. So the opposite to east is west. So my answer would be, there it is, that it's a displacement of 600 kilometers, because that's 400 times 1.5, and it's to the west because that's the opposite direction. So I hope that that makes sense, and it sort of fits with what we think about numbers anyway. So here in general, if we have a vector v and a scalar called k, where k is not equal to 0, we say that v and kv are scalar multiples of each other. So they're just multiples of each other. They've been multiplied by a scalar. Now that statement means exactly the same thing as saying that v and kv are parallel. So remember from an earlier lesson, parallel vectors go in the same direction or in opposite directions. You can think of them as parallel lines, but remember this is the vector world. So it's the same direction or opposite direction. And then an even fancier vocabulary word is to say that v and kv are collinear, which means that if we were to draw a line, both of those vectors would exist on the same line if we wanted them to. Because don't forget, a vector doesn't have a location. It has a magnitude and a direction, but we can move vectors around without changing them. So collinear simply means that they could share the same line. They could be part of the same line. Okay, now you'll notice that I said if k is not equal to 0, these things are true. So what happens if k is equal to 0? Oops, well, I gave it away. If we multiply a vector times 0, what we get is something called the 0 vector. So the 0 vector is one of those weird sort of, math theory kind of things. It's like, why does this, what? So the definition of a 0 vector, it's a vector that has a magnitude of 0 and an undefined direction. So we do say that it exists, and we do call it a vector, but, it's a magnitude of 0, and it has no direction. And there are times when you need to consider an undefined direction to mean that it goes in all directions at once. So it's like, math version of a Higgs boson particle. I don't know. But if you ever do multiply 0 times a vector, it's possible, and the result is called the 0 vector. Okay, so in terms of other issues with multiplying by a scalar, all the things that we would like to be true, things that we know from our general algebraic knowledge are true. So for example, if I have two vectors added together and they're multiplied by a scalar, I can distribute that scalar to both of those vectors. So k times u plus v is ku plus kv. So just like working in a way with variables. If I have two scalars a, b, and I'm multiplying both of them times v, then I can multiply them together first. I can multiply one times v and then the other one, so I can associate just like in multiplication. Order doesn't matter. And then of course the identity property, if I have 1 times v, that's just vector v. So all that stuff hopefully makes sense. And here's just some more examples of sort of how algebraically speaking, when you multiply a vector times a scalar, you get pretty much what you would if you were working with variables like x and y instead of vectors like I have here, u and v. So again, 6 times u plus v is 6u plus 6v, exactly what we think. We distributed it. Here I have 6u plus 5v. Well, if I have 6u plus 5v, don't I actually have 11u? Oops, I said v. Didn't mean it. You can see what I'm doing. 6u plus 5u. So I'm basically collecting like terms. 6u plus 5u is 6 plus 5u's, which we know is 11u. So again, it's like collecting like terms as if it was x and y. Here we have that associative property. If I have 3 times 4u, I could also write that as 12u. Or I could go the other way and break it this way if I needed to. And then here, I have an expression where I'm adding and subtracting a bunch of vectors. So 2a plus 6b minus 5a minus 6b. Well, I'm going to collect like terms just like I would if those a and b vectors were actually variables. So I have 2a minus 5a is negative 3a. And then 6b minus 6b is the 0 vector. So I'm not going to say plus 0 vector because it's like saying plus 0. Just like, why bother? So I have negative 3a. So all of these things should fit perfectly into what you already do algebraically. It's just we're doing it with vectors. All right, so let's just go ahead and do some math. So for example, we have a vector called u, which is 3 meters to the left. We have a vector called v, which is 5 meters to the right. And we want to find a vector represented by 2u plus 3v. So I'm multiplying my original vectors. So vector u goes to the left, and vector v goes to the right. So let me just use my tool here to draw a beautiful line. And the original magnitudes are, u is originally 3 meters, but of course we've multiplied it by 2. So it's actually 6 meters to the left. So this is 6 meters to the left. And 3v, well, v is originally 5 meters, so it's actually 15 meters to the right. So, I mean, logically, if I go 6 meters left and then 15 meters to the right, what have I actually done? Well, what I've actually done is I've done this and then this. So my final displacement is this piece here, which is 9 meters to the right. And of course, you don't necessarily need a diagram for that, but certainly, ooh, that doesn't say what I meant to say. When you're in the early days of learning something, the more you do the fundamental pieces, like drawing the arrows, the more things tend to click and make sense and be useful later on. So again, 6 meters to the left and then 15 meters to the right basically means I end up with 9 meters to the right. So the final result vector is 9 meters to the right. Let's look at another one. So what if, okay, I'm starting with the same vectors. I have a vector u, which is 3 meters to the left, and I have a vector v, which is 5 meters to the right. But now what I want to do is I want to find 2u minus 3v. So 2u, get my pens here, 2u is still 2 times 3 meters. So it's still 6 meters to the left. But negative 3v means that I'm now going 15 meters to the left. So this is not really my vector anymore. My vector is now 15 meters to the left because I made it the opposite direction with the subtraction sign. So I'm going to the left with both of my vectors. So I'm going quite a bit to the left. So what I'm doing is I'm going 6 meters to the left and then 15 meters to the left. So in total, what have I done? I've gone 21 meters to the left. So again, all of this stuff hopefully is sort of logical in what you hope it means. Let's talk a little bit quickly about some vocabulary. When we have an expression like 2u plus 3v, what we're doing is we're finding a linear combination of u and v. And I remember first year algebra at university, that phrase, whew, I feel like that was the whole course. 2u plus 3v is a linear combination of u and v. And I sort of use this word already, that the vector we obtain when we do this math is called the resultant vector. And we often denote resultant vector with R vector. So just so I can use the word resultant now. Let's do another example. So we have this hexagon, A, B, C, D, E, F. And we're told that opposite sides are parallel and equal. So AB and ED are parallel and equal. FA, DC, parallel and equal. BC, FE, parallel and equal. And we also are told that there is a line through the middle, so let me just add that to the diagram, called FC, boop, where FC is equal to 2 times AB. So that's the information I need, and then it says let AB equal U, so I'm just going to add that to the diagram. Let AB equal U, so this, actually let me add it nicely to the diagram. Just because we're going to use this diagram apparently for a couple different questions here. There. So AB, oops, AB is vector u. Okay, let me try again. Yeah, some people edit their videos, some people just keep talking. Whatever. Okay. So here's vector u, and then vector FA, so let me get vector FA going, is called V. So that's vector U in blue, and V is the red one. So we need to find a way of expressing these vectors in terms of just U, which I'll write here, and V. So the first vector we need to represent is vector CF. So CF, as we can see, goes sort of from here to here. That's vector CF. So how can we represent that? Okay, so here's vector CF. So CF is the exact opposite of FC. So we can see that FC is already declared to be 2AB. So you can do this visually, and you can also do it with pen and paper as follows. So use the pen. So CF is the opposite vector to FC. And we know already that FC is 2AB, which means I can write this, ooh, why did I do that? Which means that we can, instead of saying FC, we can say negative 2AB. And we know that AB is vector U, so this is just negative 2U. And again, you can see that in the diagram as well, the blue vector, we know that this is exactly twice and it's going in the opposite direction. So here I've done it more algebraically, and here you can do it visually. Okay, let's talk about vector FB. So vector FB, so where's FB? So let me get rid of this one, and we'll introduce vector FB. Okay, stop. Here's vector FB. So from the diagram, I can clearly see that if I add V and U, I'll have vector FB. If you want to see the algebraic sort of approach, I could say that FB is FA plus AB, and FA we know is V, and AB we know to be U. So that's that vector. So what about C? C is FD, so let's have a look for where that is in the diagram. FD is here. There's vector FD. So how do I get vector FD? Well, we can use vector we had already. We can use FC to do this, and then we can go like this. So I'm going to say that it's FC plus CD. Now, why is CD useful? Well, CD, we're told, was opposite and parallel, and the same length as vector FA. So we can use V here as well. So algebraically, I'm going to write that FD is equal to FC plus CD. And hopefully you can see that visually you know that, because FC plus CD, C, if I go through C, I could ignore the C and say it's FD. So, you know, you don't always need a diagram. So FC we already know is equal to 2AB. And CD we already know, why do I keep writing equals? FC we already know is 2AB. And CD we are told is, well, we're going to write it's the opposite of DC. Oh, and I didn't do that. Sorry, guys. Okay, here we go. CD is the opposite of DC. And I'm doing that because DC is the same thing as FA. So 2AB is 2 times vector U. And negative DC is the same thing as positive FA. So it's 2U minus V. And again, you can get all this by drawing on the diagram, but I just want to show you, you can also get it in a more algebraic way, that we don't always need to have the diagram. What else do we have to do? So we have to do E, so I'm just going to erase a little bit here. It's getting kind of messy in this stuff. Bye-bye. Bye-bye. Sorry, I don't have time to like do the edits. As some of you know, sometimes making the video and editing the video are 2 very different time frames. Yeah. Okay, so let's do E, which is EB. So what do we know on anymore? I'm going to get rid of this guy. I'm going to get rid of this guy. And let's redesign this one. So we need to go from E to B. So there's EB. So how are we going to represent that? So you may already be able to see that it's basically vector V, but longer. How much longer? We'll see in a second. So I'm going to do this one more algebraically in this case, just to keep the diagram neat. So vector EB, I'm going to go ED plus, hold on, where's my notes here? I'm getting a little confused. ED plus DC plus CF plus FA plus AB. Now, what the heck did you just do, Miss Townsend? Well, what I'm doing is I'm only trying to use the blue arrow direction and the red arrow direction. In other words, I don't know anything about EF or BC, so I don't want to use them at all. So my path to get from E to B is basically this path, and I'll just sort of use a thicker pen just to really emphasize what I'm doing here. Visually, I'm doing this. I understand this distance. I understand this. I can't take this shortcut because I don't know anything about that vector. So I'm going to go all the way across like this because I understand that, and then like this, and then like this. So if you know, you started at E, as long as you eventually get to B, you're doing vector EB. We took a long path because we had to avoid vectors that we don't know. We can only use vectors we know, which were vectors U and V. So now that I have this, now I can start to say, okay, well, what does that actually look like? So ED. So ED was this vector, and that's the same as vector U. DC is this vector, which is the same as vector V. CF, so we've done CF before. It's twice the length and the opposite direction of vector u. FA, well, that's defined as vector v. And AB is defined as vector u. So you can see you have to use the vectors you have, but then it's just, okay, well, let's just, oops. Ooh, that was almost very bad. Sorry, that was CF, which was twice the length. So now I'm just going to collect like terms. U minus 2u plus u, so I don't need vector u. It's just 2 times vector v, which we sort of saw from the original diagram. And then, of course, F, if you've done E, F is very straightforward. EB and BE are just opposite vectors, so it's negative 2v. Okay. So, again, visualizing and being able to write the algebra, both important. Remembering that when you're adding vectors, you know, when you have given vectors, you can only use the given vectors. I don't know how to define this vector or this vector. Like, I don't know how to talk about those. And I certainly don't know how to talk about, say, the path from B to D directly. I have to follow these paths. Ooh. All right, let's look at this one. Ooh. So back to something more arrowy. So we have 2 vectors. One is vector u, which is straight north at 50 kilometers per hour, and one is vector v, which is straight east at 80 kilometers per hour. And we want to find the linear combination 3u plus 5v. So obviously 3u means that I actually have straight north at 150 kilometers per hour. And 5v means that I actually have straight east. 5 times 80 is 400. So I need to add together these 2 vectors. And obviously, really importantly, you learned this yesterday, when you add vectors together, you have to add them tip to tail. So that means, I draw a lot of diagrams, so stay with me here, that if I first go north 150 kilometers, then I go east 400 kilometers. So you can see here, I've got tip to tail. This is invalid adding. There's no such thing as this as a resultant vector. That doesn't make sense because you go this way and then you go this way. You don't go this way and then magically, through the magic of Doctor Strange and Harry Potter, go back down here, right? Think about it. Okay, so now we know that the resultant vector is this vector. It's the vector that goes the shortcut between the 2 actual vectors moved. So that's vector r, because I can now say resultant vector. So let's talk about the magnitude of vector r. Obviously, the magnitude of vector r, remember the notation for magnitude, we're just going to use the Pythagorean theorem. So it's 150 squared plus 400 squared, and then I need to square root that. So the magnitude of vector r is, hold on, magnitude of vector r is 427 kilometers per hour. I just rounded. And then we also, obviously, I can't stop there. I wanted the vector, not just the magnitude. So I also need to find an angle. And you'll remember from one of the earlier vector lessons that we like to describe, when we're describing north, south, east, west type vectors, we want to describe them with reference to north and south primarily, which means I want to find this angle. Also, this is the direction it's heading. So finding this angle here would be very confusing because that's not the heading of it. So I need to find that angle, so we're just going to use tan. Tan theta is 400 over 150. So theta is about 69 degrees. So I would describe vector r as a vector with magnitude 427 kilometers per hour. And the direction is north, 69 degrees west. Nope, east, my bad. Ooh, I'm really bad at east and west. And again, it's because if you go due north, that's more appropriate than going south. But don't go due north. Instead, turn towards the east by 69 degrees. That's what that says. We learned that earlier. I just want to review. And so now let's look at a much more complicated one. Still involving resultant vector, still involving north, south, east, west. But not just pure north-south. So we have vector A with this magnitude of 70 kilometers per hour, and it's going in direction north 20 degrees west. Oops, I forgot to write in the little degree symbols. So I'll just pretend. There we go. B has a magnitude of 80 kilometers per hour in a direction of south 35 degrees west, and we need to find 6A minus 2B. So obviously the first thing I'm going to do is I'm just going to adjust my magnitudes here. It's not 70 kilometers per hour. I'm actually working at 420 kilometers per hour because it's 6A. And then a direction B has a magnitude of 80, except for we need to adjust that because it's 2 times that. So that's actually going to be 160. And then don't forget it's minus, so we need to adjust what direction it's going. So first of all, let's look at these directions to begin with. So vector A is going north, but 20 degrees towards the west. So that blue arrow represents the true direction that we want to deal with, and it'll be at a magnitude of 420. However, this direction, south 35 degrees west, so due south, not quite, go 35 degrees towards west. That's vector B, but we need to take the opposite direction. So the opposite direction would be exactly 180 degrees from it. So it would be that way. And then what would that angle be? Well, we need to remember, some fundamental geometry, that we have opposite angles here and here. So that's also 35 degrees. So now I have a better feel for what's actually happening. So now I'm going to visualize. So this is where you're going to see Miss Townsend's drawing a million times. So the first thing we're going to do is we're going to go north 20 degrees west. So what I do is I draw, actually I need more room here. Let me go to a new screen. Oops. Hi. See you in a second. So what I do is I do this. I draw myself the little north, south, east, west kind of crosshairs. And then I say, okay, we're going this way. And I write to myself that it's 20 degrees, right? North, 20 degrees west. And the magnitude of this was 420, right? Let me just double check that. It was 6 times 70. Yeah. So that's the first vector. And then, oh, I still didn't give myself enough room. Hold on. Move everything down a little. And then what I do is I draw another little crosshair. And this is sort of my best advice for how to deal with this sort of thing. I'm going to draw another little crosshair here, and then draw the next vector. So the next vector goes sort of up and to the right, like this, and this was 35 degrees. And the reason why that little vector thing is important, well, I mean that little cardinal arrow thing is, you'll see in a second. So then I'm going to draw, well, this is therefore the actual vector that we want to discuss is this, oops, bye, thank you, is this vector, the resultant vector. So how are we going to talk about it? Well, okay, so first of all, I'm going to add back into the diagram the fact that this was, I don't remember, 160. So this was 160, the magnitude of this. This was 420. So obviously you can see a triangle, but it's not a right-angled triangle. But here's the magic trick, and it's not a magic trick, it's just we know math. If I trace this out, so this vector here, I'm trying to do it carefully. See that Z pattern I just drew using the cardinal north-southness? That Z pattern tells me that if this is 60 degrees to the black cardinal direction cross, then this is also 20 degrees. And actually, let me draw that with straight lines just to really send that home to you. So there's a north, south, east, west, and there's a north, south, east, west. And so let's say we have a vector between them. Let's do this one. So if I have a vector like this, then there is a Z pattern because of parallel lines, because we know that this, we know that this north-south line is parallel to this north-south line, which means that if you turn your head, you can see a Z, and that Z is right here. There's a Z, long and narrow, it looks like this, right? But it's a Z, and the elbows of a Z are equal. That's how I knew that, because this one's 20, then this one's 20. And what's really important down here is that I'm drawing that 20 degrees to, not to the red resultant, I haven't looked at that yet, but to the cardinal direction thing. And that means that if I know this is 35, and I know that this is 20, I actually know what this angle is. So that must be 125 degrees because I've got a 180 line right here. So what I have, and I'm just going to keep drawing new diagrams. Don't worry, I do the same thing on the chalkboard. I draw about 4 diagrams. Is I have a triangle that looks like this. I've got 125 degrees right here. This is 120. This, was it at 120? Sorry, or 160. You gotta get that right. Okay, it's 160. This was 420, and I want to find this. So I can find the magnitude of the resultant using cosine law, because I have these two sides and the contained angle. So using the cosine law, I can calculate what's in between them. So 420 squared plus 160 squared. Oh gosh. I might have to re-release this question in neater form, but yeah, it's good stuff, right? And then when I calculate it, what do I get? So 420 squared plus 160 squared minus 2 times 160 times 420 times cosine 125. Take the square root of that bad boy, and I get that the magnitude of vector r is 528 kilometers per hour, which is great, but I need more than the magnitude. I need to find the direction. So let's go back up here to this diagram, and what we really want to do is we really want to zoom in right here. Let's see if I can get this one working. Ooh, look, I'm zooming in. Now, I'm zooming in on something messy, but what I want you to do is recognize that I need to find the direction of that red line because it's my resultant vector. And that red line is obviously north something west, so I need to figure out what that angle is. So the key is we're going to return to this, and we're going to find this angle here, because that's, oops, forgot to go back to regular pen. Yep. Yeah, that's the irregular pen. It's called Magic Pen, and it's slowing my computer down. How's everybody? Good? Okay, now this is annoying. Okay, you fixed it. Nope, didn't fix it. Oh, I'm sorry. You're 32 minutes in, and if you're still watching, I'm sure you're frustrated as heck. Okay, so we need to find this angle. So let's start by doing that. So we're going to use the sine law. So sine 125 over r is sine theta over 160. So calculating theta, so sine 125 times 160 divided by 528. Inverse sine that bad boy. And I get that theta is 14 degrees. But be careful. So now I'm going to draw one of my much more carefully designed diagrams. So remember how we zoomed in right at that corner, and we had the original vector going north 20 degrees west, sort of like this, and we knew that we had 20 degrees in here. And then we also were like, we had drawn the red vector, the resultant vector in red, and it looked like this. So again, I'm just zooming in, right? But I'm doing it neatly. Well, now we know that the angle here in the actual triangle is 14 degrees. That's the angle we know. But if I want to describe the red resultant vector, how do I do it? Well, remember, this blue angle is 20 degrees. And this red angle is 14. So what is this angle, the angle I actually need? It must be 6 degrees, which means that the direction of the resultant is north 6 degrees west. Fun stuff, right? Oof. God, math is great. Anyway, there's the guy that no one's told me his name yet, or what he's from, or why I put his picture up. But I hope that was useful. I'm sorry that it was such a mess. I will try to create a better version of that sort of question. Bye-bye.